Hello everyone, welcome to another stream. My USB cable disconnected and I'm back. How are we doing? How's it going? So yeah, today we're going to be recapping the BVH construction process. So we're going to talk about everything that we're doing to build a BVH on the GPU. Right now, I just need to fix one bug, and then we'll, yeah, it's clipping a bit. Hang on a minute. So why is it clipping? I need to increase the size of the where is it? Yeah, so in the nodes, when we pack and unpack the half dims, we need to increase the resolution. No. Yeah, we need to, rather than being an unsigned norm, we're going to make it 0 to 2. Oh, for crying out loud. Right, that's a bit buggered. Again. Okay, that should be back. Just gotta be careful with this, you see. Right. Any movement of the table was messing around with it. Right. Maybe that's alright now, I don't know. Just make sure. Messing up. I need to get a new USB hub, I think. My cables, I don't think it's responding well. It disconnects a lot. Right, so basically we've got when we make a BVH node and we pack it down, I think we need to clamp it from 0 to 2, and then we times it by 0.5, right? And then we multiply it by this, so then it will be 0 to 1. And we multiply it by this number, add 0.5, and then convert it to an int. So I think that will be the fix. We've got to store 0 to 2. So it won't be unorm anymore. But I just want to double check and make sure that... See, I don't think I need... Where's that code that we did? Where's that draw vector at? Yeah, let's get rid of that. Right, so I think this should be fix all our problems with the trees. No. I wonder how those things being drawn. Oh, they're drawn in the ray tracer, those ones are. So if they're going from 0 to 2... Right. They're half the size still. When I extract them back out, I'll multiply them by 2. I think that's it. So it won't be uninorm anymore. Right, this looks better. So the outlines are the parent nodes in the tree. So it's quite difficult to tell which one is which when there's so many, but when you bring it down to a simple one. So there's no parent nodes in the tree. There's a root node. We don't have root nodes in our packed tree. We just have the first set of child nodes. So here's what we're seeing here. We can increase up to 5 leaf nodes. Therefore, you need another parent because we're going to allow at most 4 children. So these 4 children go into here. The parent one is this third one here. And then 8 is this one. See, as we increase. So this is with 3 in one side. Right, 3 here, that's 2. And then there's 4 here, and this node is 3, which is this blue one. So it's still not right. Still not big enough. Yeah, I think it's got to be that square root of 3 thing. I put square root of 2 just to try it out, that's why. Let's try that again. Okay. So they're going to be like way bigger now. But hopefully it doesn't cause any bugs. Yeah, obviously we want to have probably a tighter fitting algorithm, but I want to work on that later because I'm not overly fussed at the moment. I think I'm more fussed about other features first. We can optimize the size of the ellipsoid parents. Just got to make sure it works. That one looks like it could fail, right? Yeah, what's going on there? This red one ain't big enough. Oh no, this one's part of blue. Yeah, I remember seeing this one before. So blue, yeah, red has 2 of them. This one here and this one down here. Whereas these 3 are actually, this one's inside the blue one. This disc here. So that makes sense. So, yeah, there's not an angle where it clips anymore. Okay, that's cool. That's very nice. So we can increase the number of leaves and just analyze the tree a bit more. So we added another, oh, I didn't add another one there. Where it's got, alright, it's got 3 nodes in 2 now. Yes, 2 is this red one. And none of those really going outside. None of these really going outside either in this blue one. So they're all in there, which is great. Let's go up again. Right, so this orange one has 2. You can tell they're here, right? There's one of them has 3. There's another one by itself. And there's one with 2. quite difficult to tell what is what. Well, that's the one with 2. There's one with 3 here. And this one here is outside of all the others. But it's the same. It's a sibling with 3 and 4 which have children. So it's a sibling with these 2 blue outlines. Is that one there? That leaf node. Cool, so I think what we've written is good enough. Let's just keep going and double checking though. And then what I would like to do it's like a little UFO. Oh, maybe not. Cool. I wonder what the performance is like. It's got a bunch of... It's definitely not been optimized yet. But yeah, there's all the nodes. Obviously, if we get too close and we go inside one, that's not good. We should probably look into figuring out how to fix that. It might not be too hard, right? If you hit an ellipsoid, it's quite easy to figure out. It's in the reverse ellipsoid code. So basically, right, reverse ellipsoid outline. It's not that one, but it's his buddy. So basically, this code here gives you t. This gives you nearest t. This gives you furthest away t. So how far you need to travel along the ray until the hit. But there's this thing that happens here where it calculates a miss. And I think it could be... See, if it's here, it's a bit more problematic. But if it's here, then your t is just going to be negative, right? And I think... I have a feeling that it could be here. No, but if you're raised inside... Yeah, you should be able to at least see the back. So what we're going to do is we're going to say... Let's just give it a go and just say if t is negative... Try the back. But that's not a good approach. In the long run, I just want to see what happens. Right, we seem to be able to go through here now. Yeah, that's good. It's working. But obviously the t is wrong, so we're getting weird looking thingies. So that's cool. So basically if it's negative, you want to output 0. So you max it. So I'm going to call it t near just so it's more readable. Then I'll make another one called t, which is max f32 of t near and 0. And then that just makes a ton of sense, right? So the person reading that should be able to understand why that exists. So let's just move up here and see what's going on. Right. Yeah, you're not going to get... The normal you're going to get will probably be a bit weird on that, actually. Think about it. Well, it's better than what it was, right? Disappearing was far worse. When we have like proper scene, I can investigate this problem a bit more later. So let me investigate. Yeah, I think that's all the little bugs we wanted to fix, because now we have a proper implementation that works. So I think we might go over how this BVH construction works. Yeah. Although I do want to record an intro and talk about this. So I think I need... So how about I only show this when this tree is up. Yeah, I only show the outline when the tree is up. Maybe something like that. How can I do that? Well, ray tracer. It's a lovely ray tracer. We didn't really check the performance of what it was like, but it's probably not a good idea to do that yet anyway. Well, let's just see how bad this one is with such few nodes. Might be interesting. Probably quite meaningless, but still a bit of fun. So enable the profiler. Right, so the profiler says that it takes 0.7 milliseconds from here, but it jumps up to about 1 something. But as we get closer to a full screen, it's about 1 millisecond. There, you can see it. It's this one here in it. But that's only 32 nodes, right? And as we increase, it's about 3 milliseconds, all of that to go through. So yeah, we've got a lot of debug stuff in there at the moment, but okay, good to be aware about that. And I guess if we take out this extra ray trace here, which is the outlines, maybe, I don't know what you get. Let's have a look. So there's tons of optimizations we can do. Currently, we've got some big expensive PBR code which runs even if your other threads are traversing down the tree. It's horrible. This one's 5 milliseconds. What did I say it was before? I don't remember. Well, that's not really a fair comparison. I'm not sure the exact distance away it was. But anyway, yeah, part of the problem with the existing code is as we're traversing down the tree, we're checking all the children, and we ray trace against an ellipsoid. And if it's a parent node, we should just put it on the stack and go. But then if it's a leaf node, we do a full-on shading, like PBR shading. So obviously, both of these branches can run. Both of these branches can end up running across 32 threads which are in the same wave. So we should probably do a cheap operation like putting it on a stack somewhere, or a cheaper operation by putting it on a stack somewhere, and then at the end of the shader batching all of those PBR calculations. I think that might be better. Right. So I want to put an if statement in for this. How would I do that? Well, in my globals, my global buffer, I'm just going to whack a boolean. Let's say mouse is locked. Right, so is mouse trapped? That'll be the condition. So basically here we're going to say if gfx global is mouse so I think is it if it's trapped. I forget what it is, but yeah, we'll put that in there like that. Then draw those lovely outlines. No, it's the other way around, isn't it? Of course it is. Cool. So that works. Right, so let's get started on the recap, I reckon. Hey, Redact. How's it going? Would you like to check out my Rust maldev blog post I wrote some hours ago? It's my first web dev and blogging ever. Yeah, I know, like, what's the topic exactly? Because web dev is something that's like not really my jam. I used to do it. But not anymore. I used to program Rust, but not anymore. Amazing. Basically, it's a post about me reading and refactoring some malware code and dunking on the author. Oh, okay. Yeah. How about if you send a link, I'll take a look sometime. I'll give it in my browser. Sounds quite interesting. Yeah, send it in the chat. Put it in Twitch chat. Source code. What about the blog post? There we go. Yeah, that went a bit wrong, didn't it? My dark mode. What's going on? That slight gradient ruins the dark mode. Yeah. Great. Yeah, I'll take a gander. Is this the one? I'll take a gander. Right. So we've got to talk about... Oh yeah, what did past Henry do? It's always good to check on past Henry. Vode? VOD. Make sure past Henry is okay. No, not VOD. Sorry. That's kind of present Henry. We're talking about proper past, summarized Henry. Here. See, past Henry is like within a new renderer. So what did I say exactly? I drew a BVH, talked about top level, bottom level, didn't I? And I was talking about why I didn't like my current renderer. And this was 3 weeks ago, or 2 weeks ago. And in 2 weeks we built a BVH constructor, oh yeah. Oh yeah. Oh yeah. Thank you, Davros. I was looking at my laptop by the Twitch chat open here. Yeah, PBR's looking good. I like it. I just got the standard, box standard implementation. I think I'm using Oren Naya for diffuse. So that's not Lambert. So it looks a bit better. A little bit more expensive though. But yeah, it's gonna hopefully look nicer when I use a lot more bigger shapes now. So I've got ellipsoids, so I'll be able to produce bigger surfaces, and I can even produce flat surfaces really, if they are an ellipsoid like this, right? They're kind of flat. So yeah, probably gonna go back in and tweak it at some point, the PBR, but for now, good enough. Should be able to build some models. Gonna be legit. Gonna be legit. Yeah, or no. Does look better. I think there's other ones you can use as well. Someone linked to the AMD material thing, because they did that open material graph thing and they've got a bunch of functions in there. There's some more in there. Don't have PBR in your engine yet, just old school specular maps and generating cheaply used diffuse textures. Yeah. Well, you know, it's always something you can add on later. You know, unless you've obviously set a bunch, put a bunch of time in to make your game look a very specific way, you can't obviously just chuck it in later. But if you still got to do another pass on your rendering, yeah, you can always just add it on later, basically. Have you got a link to any of your latest work? Because I remember seeing it before, and you had this sort of vehicle thing, and yeah, IK as well. I think quite crazy. It's awesome. I'll balance my look around some improvised assets, so it's not trivial to go in and add it, but it's not impossible. Oh, okay. Let's take a gander. It's alright. Cleaned up the SSAO a bit. Cool. Right, luckily I didn't get exposed. What's in my downloads folder, eh? Right, I gotta take this in. I have to watch it back again. Neat. That's cool, man. There's a lot of work that's gone into this. Yeah, you had that vehicle last time, you got this thing as well. It's crazy. There's a whole bunch of them. And then you can get in one. Incredible. Clean up this a bit. I need to make another video as well. I tweaked water blending and added some minimal foliage. Oh, cool. So you're making look a lot less sort of textured ground and put some more stuff on it. Awesome. Yeah, you've definitely got that sort of like early 2000s look. Is that right? Early 2000s to the game right now. Brings back memories of playing PC when I was younger. I didn't play first person shooters though, because I was obviously quite young then. But I did play a bunch of other games. Xbox 360, oh, and slash 360, right, yeah. Awesome. Bum, 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 bum. So past Henry talked about BVH built BVHs and what they are. So this Henry is going to talk about what we've done and how to build a BVH. There's specular maps and hadn't generally gone full PBR yet. Yeah. There was yeah, there's another type of specular and yeah, maybe I misremembered something. Okay. It's recorded. Oh. Right. Hello everyone, welcome to another devlog. So over the past couple of weeks, we've been building a BVH constructor on the GPU. So what you're looking at right now is a bunch of ellipsoids, which is the new rendering primitive we're using. And we're ray tracing against a BVH, which has been constructed on the GPU, which houses these ellipsoids. So right now, these are randomly generated within a assigned norm region of -1 to 1. And so they obviously don't look too appetizing, but they've got PBR on them. If we escape here, what we're seeing is the outlines of the tree, the parent nodes, and this is a debug version of the tree here. So up here we can turn down the number of leaves and then also up the number of leaves as well. And we've been using this tree visualization here, as well as these debug drawings to sort of help debug the code that I've been writing when constructing these BVHs. You know, I'm going to do this again. There's just tons of information in the face. I think I'll describe it in more detail piece by piece. What is that tree? It's a bounding volume hierarchy. So, negative values. That ain't good. I know the exact problem that's causing that. So yeah, bounding volume hierarchy. So it's with 4 children. It's a little bit of a special version. T far, T near. We want to. Did we just clamp it? Or yeah, clamp value of near to at least. No, I gotta put if statements in, I think. So if T far is less than 0, then T far, or then T near, if not T near max 1, something like that. It's pretty crap, but let's do it. What kind of monster makes grey Skittles? Yeah, well, I guess they did like grey Skittles, eh? Great, so they don't show up behind the camera anymore. And you can go through them as well. Just got my head inside of an ellipsoid. At least you can see something. Cool. Right, let's redo that intro because that was silly. It's like a blurred HDR. What do you mean by HDR? Oh, you mean the environment map or just in here? Hello everyone, welcome to another devlog. So over the past few weeks we've been building a BVH constructor on the GPU, which will construct a tree of ellipsoid nodes, where the leaf nodes are these ellipsoids here that we're seeing on screen right now. So we're currently ray tracing this BVH tree, and this is currently the bottom level BVH, where it is just a single instance right now. But yeah, we've got a nice little debug visualization. We visualize the tree that we've built, which we'll go more into in a bit. And we've also got this debug visualization of the parent nodes and how they wrap around the children. And we can change the number of leaf nodes here from about 4 all the way up to 64 here. So this is what we've tested so far basically, and it all works out. So let's jump into the details. Cool. That's good. I like. Yeah, it's the you see the environment map in there. We've got it's PBR, right? So the specular reflection shoots out to the environment map. And then when you go inside, you really see it. Probably because the way the reflect function works. I don't know. And the normal's a bit wrong, to be honest, when we're inside. But we should not really encounter that anyway. Which should be good. Which should be good. So what should I talk about first? Should I talk about the way I started off or should I talk about the algorithm? Yeah, I'm gonna do a high level overview of like what was built first, and then we'll go into the details. I think that is probably sensible. That is probably sensible. So no draw, no dispatch. So here's all the compute shaders. Right, sort your leaf nodes. Then we uniqueify it, the Morton codes. Build a binary tree, build a quad tree, then we pack our quad tree. I think this is just too much to talk about. Or yeah, maybe we go over Morton codes first. And then, or do we go over the... Right, here we go. Right. So the first thing I did, right, okay. Right, so before I implemented this on the GPU, what I actually did is took the paper, which we'll get into in a minute, and implemented it on CPU side. And what it does is it will construct it just the same sort of way it would do it on the GPU, where it's very independent. That one again. Right, so I want to show you the paper that we implemented on the GPU, but before we get into that, I want to show this debug visualization here, because it's very important on how we actually managed to debug it and make sure it works before we ported it to GPU. We implemented this on the CPU. Now, one more time. That was just so funny. Right, so what we've got here is this debug visualization, and it's all done on the CPU. So before we implemented a paper that has a highly parallel algorithm that constructs a BVH on the GPU, we actually did it in a very similar way, but on the CPU instead, and used the debug drawing API that we have to construct this tree. And the tree would only be correct if the algorithm worked, basically. So up here we've just got a slider, and we can just choose how many leaf nodes that we have. So here we've got 4, and it goes all the way up to 64, and it just draws the whole tree. And so there's a lot of, just making sure every node was there, and just making sure everything, there's no bugs, basically. So this is a binary tree, but also there is a quad tree version. So rather than having a parent node which has 2 children or 0, instead this has 2, 3, or 4 children for a parent node. So the reason why I did it this way is so that we could fit, when a parent node points to an array of children, all of these children nodes will fit in a single cache line. So hopefully it will be more performant, basically. Because I'm thinking, if I've only got a couple of nodes in there, I could probably, in 64 bytes, I think I could fit 4 nodes in there, and therefore operate on all 4 of them. And then the bottleneck will be the code that runs, hopefully, rather than memory accesses for a bunch of nodes. So that's the trade-off I was trying to make with this implementation. So this quad tree version is built from the binary tree version, which we're going to get into how that is done next. Maybe I cut that off a bit too quick, but I think it's good enough. Yeah. Quad tree. So how does one build? So I dropped these links in the chat for people interested. This is what we used. There's also an implementation on GitHub as well. And I've lost it. Yeah, this is it, isn't it? All right. So this is where it gets crazy. So I'll leave these links down in the description. There's basically this NVIDIA blog post which talks about how to construct a tree on the GPU in a highly parallel fashion. And then it also links to this paper here called Maximizing Parallelism in the Construction of BVHs, octrees, and KD trees. And there's also a GitHub link to an implementation here which someone has done of this same paper here. So you can use that as a reference as well to help understand it. But I want to give a brief overview on how the whole system how my whole system works, and also how this paper kind of works as well. So the first thing you need to be aware about is this thing called Morton codes. So one of the first things you need to do, or the first thing you need to do when you construct a BVH, is you need to figure out, of all of your primitives that you're trying to render, so here it's got triangles, we're using ellipsoids, how do we quickly work out which ellipsoids are near each other? And then when they're near each other, we should be able to construct a tree based on the ones which are near each other, right? So the ones that are close to each other in 3D space should be kind of close to each other in the tree hierarchy as well, right? And this is what Morton codes will help you do, or the Morton Z order it's also referred to as. So effectively you take a 3D coordinate, X, Y, and Z, and you interleave all of the bits. So there's a 30-bit version, and I think there's a 63-bit version, but we're only using a 30-bit version because we only have 32-bit integers on the GPU. So basically you take your X, Y, Z and interleave all the bits. So ours is in signed norm space from -1 to 1, and we're going to take that floating point value and convert that into an integer from 0 to 1023 inclusively, right? And that's 10 bits. So basically those bits get interleaved on the X, Y, and Z. So here you see PX, PY, and PZ, and essentially it's taking the first bit right from every one, and that's so 0, 1, 2, and then it takes the next bits here, 3, 4, 5, right? 3, 4, 5, 6, 7, 8, right? 6, 7, 8. So it just interleaves them and produces a single 32-bit integer with 30 bits being used for the Morton code, right? So just 3 10-bit numbers being interleaved. So just by doing that, you're instead going to convert a 3D coordinate into a 1D coordinate where it's actually ordered in this Z order, which is pretty clever. So with the Z order, this is 0, 1, 2, 3. So there's your first Z. Your next Z will go onto another and start another Z. 4, 5, 6, 7, right? And then after that go to another Z. 5, 6, 7, 8, 9, 10, 11, 12. So what's interesting, wait, did I count that wrong? 10, 11, 12, 13, 14. Yeah, I counted that. I still have a take of that. Right, so with the Morton codes, now it's I don't know what I did now. I said 1D and converts to a 1D coordinate. So if you take a look at this here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right, so, okay, no, do that again. Right, so it converts that 3D coordinate into this 1D coordinate. So rather than just being a lookup across the X and across the Y and across the Z, it's instead in this Z order. So 0, 1, 2, 3, right, there's your first Z. 4, 5, 6, 7, there's your second Z. 8, 9, 10, 11, there's your third Z. And then 12, 13, 14, 15, and there's your fourth Z. So you'll notice that there's this sort of micro Z that goes on and repeats. And then there's also a sort of more macro Z that happens. So after this one finishes, the next one starts here. And this whole macro Z gets repeated up here. And then after that macro Z is done, there's another version of it here. And then there's another version that goes on here. And then after these 4 have done, that's an even more macro Z, and that gets repeated in that same sort of Z fashion. Now that's in 2D, but it extends to 3D as well. So rather than going up here, this would actually do another slice in the background instead of going up. But the same sort of logic applies, but just with 3 dimensions. So, right, what am I going to say next? I've lost my train of thought. Yes, it's going to be amazing. So, the least significant bits, if you will, of the integer, these are going to change. These are going to be related to, so the first couple of bits will just be like, just control like this part of it, right? And then the next couple of bits after that, wait, where's an example? Let's go back. Yeah, all right. Right, so another thing to be aware of with the Morton codes is the sort of the least significant bits. Basically, the first couple of bits, right, already the first 3 bits in 3D, but just say in 2D is the first couple of bits. This does this, like this super micro, right, the smallest part of the Z curve. So it just controls like within a 2x2 where you would be. So it'd be like these 2 or these 2 or these 2. And then the next couple of bits after that would be the next sort of macro. There's a better way of saying it. So you can essentially see it as a tree, a hierarchy of these sort of Z curves in a sense, right? Where essentially you've got these, this is the most smallest level where it's controlling where it is within a very small region. And that'll be the first couple of bits, right? And in 3D it'll be 3 bits, but let's just stick to 2D as an example. And then the next couple of bits would end up controlling which one of these Zs it's in, which one of these groups of 2x2 is it in, right? So in this case it's 0, 0, so it actually just belongs to this one. But if it was like 1, 0, it might go over here, or might go over here actually. There's a better way of saying that, maybe. Right, so key things to take away is that you can imagine that these Z ordering or Z curve things, right? There's like a tree of Zs, right? There's a sort of the most lowest level of Z where it's just 1 2x2, and then essentially like that there's groups of 2x2s, right? So in this 4x4 there's a 2x2 set of 2x2s, right? And that's the next layer. So you would jump between either this one, any one of these groups, and then there's a layer above that where there's this tile, and there'll be another tile over here, another tile up there, another tile up there. So each one of those is controlled by the bit pattern. So the first couple of bits will control this tile, or this within the most smallest region, smallest layer of the tree, which one of these cells you're referring to. The next 2 bit patterns will refer to which one of these more macro cells you're referring to, right? This macro Z. So imagine if this had a 1 or sorry, maybe like a, you know, like a 1 and then a 0 there, you would go up to here, right? Because that's your next sort of Z in the tree, in a sense. And then these guys here, which are 1, 1, so technically you would probably be over this side, because 0, 0 will put you on this group of 4x4, 1, 0 put you in the next group of 4 up here, and so on until you get to there. So the key thing to take away is for every one of these bits kind of represents a different axis, if you will. Wait, what's a better way of saying it? Each bit, because that's like y bit 0. So each bit, okay. Right, so key thing to take away is that each bit will essentially just change, you know, the lower, the least significant the bit is, the more sort of close to the change, the closer they would be in 3D space. The closer they would be in 3D space. But the more higher the bit pattern, the more it changes in the higher bit pattern, the further away they will be. So if they change here, they're going to be in one of these different 2x2s. If they change one of these 2 bits up here, it's more of this 4x4. Each one is 4x4s, so they could be near each other, but also they could just end up being quite distant. And obviously the higher the bits, the more further away it could possibly be. So something to be aware of. Oh, that's it as well. And there's also another thing to be aware about is if this one here is 8 or 7, right? So that's the first 3 bits on. When you increment, all those bits will turn off and turn that bit on and go down here. It's something to be aware about, that whenever all the bits roll around and down to 0, you get a big jump like this, right, where it just jumps. So you've got to be careful also with a Z curve, just because it might be next to each other in a sorted array, that it won't necessarily be next to each other in 3D space. So that gets into the next topic, is once you've converted all of your, I'll get back to that one in a minute. Yeah, let's show the code and we talk about what do we do with it. Yeah. All right. So if you scroll down on the blog, it literally gives you an implementation here of how to implement it. It's nice and easy. Again, you're taking your float X, Y, Z, and here it's treating it as if it's in like a 0 to 1 range. So just multiplies it by 1024, and then it will essentially expand the bits, right, and interleave the bits as well. So after you've got your Morton code for every single leaf node, or ellipsoid in our case, or it could be a triangle, what you need to do is you need to sort that array of Morton codes, or you need to sort your leaf nodes so that they are in order. So when you've sorted your Morton codes, all of the nodes that are next to each other in the array are likely to be near each other in 3D space as well. So this method alone kind of solves that problem where it's like, how do I take all of these objects which could be presumably quite, they could be all over the place in the scene. How do I very quickly, or in a very nice and simple way, work out which ones are near each other? Well, the easiest way is to sort them and then turn them into this sort of like, after turning them into this Morton code thing. So there's a little thing to be aware of, and that is this cell here would be 7, right? 0, 1, 2, 3, 4, 5. Wait, 0, 1, 2, 3, 4, 5, 6, 7. So this would be 1, 1, 1, 0, right? So when I increment this by 1, it would turn all these to 0 and put this bit to 1. And that'll give you 8. Right, so when you sort of roll all those bits back to 0, and obviously the higher it gets, the more of a jump it would be. But when you roll those bits back, there's going to be that jump. So just because it's next to each other in that sorted array does not mean that it's next to each other in 3D space, but they're more likely to be. So yeah, I was holding myself there because I was thinking about to say something I didn't quite sure about. Hey, Code Nugget, you plan for static geometry or dynamic? So currently it's static, but with dynamic, there's a thing called BVH refit or refitting. And basically you just start at all the leaf nodes and you just traverse up the tree. And you refit everything such that, so you move your objects around the scene, or you skin your mesh, and then you traverse up the tree again and you refit the parent bounds around where the geometry is moved. It does cost, so with ray tracing you have a very limited amount of dynamic instances, but it's possible. So you've got to be careful. We shouldn't be having too many high numbers of geometry anyway, so it should be okay. Plus we're not going for too much of a fast-paced game also. So yeah. Other APIs like Vulkan, they called it BVH update. Not the best name, but just so you're aware, it's also called update. So refit is the name I typically like most. Would it be faster than a plain AAVB K-drop where needed? What do you mean? Sorry, K-dop. What do you mean by K-dop? Is a Boolean intersection of extents along K directions thus. Interesting, I've never heard of this. Oh. Right. Okay, I think I get an idea what's going on, but not really. Review for us some tests, okay. Yeah, I've not heard about this before, to be fair. I don't know why I've not heard about it. But yeah, I might read about it some other time. Never heard about it. But yeah, with the BVH, it's used typically everywhere for ray tracing anyway. Fastest way to do ABB first, and then you work through the other axes when you have sufficient overlap. Right. Is there like a dop in it? Someone done it in Shader Toy. Don't think they have. Want to see an example? Oh, you're talking about when building the tree. But yeah, the Morton Z order you only do it when you build the tree once. You don't do it when you refit. Like you only recalculate the bounding boxes. What am I looking for? Oh, this K-dot thing. Do you use it for like intersection test? It looked like you did. Alright, nothing on Shader Toy. Can't see. I'm just not sure if I understand what it is exactly yet. Right, I was about to say something where... And I stopped myself from saying I said so. Oh well. Right, so should we talk about a little bit more about this paper? Yeah, once you have your list of Morton codes. Oh yeah. I can talk about my Unifier shader. Right, AMD Fidelity FX sort, what's it called? Yeah, this is what I used. Is this the old one? Oh yes, an error in it. Right. So a month or two ago, I poured Fidelity FX parallel sort to my codebase. I recommend it because it's open source, and you can, I poured it to my custom shader compiler HCC, and it went quite smoothly, and it's all pretty good. But you don't have to. If you don't have to sort your stuff on GPU, you can just sort it on CPU and upload it to the GPU. But so my code base, one of the first things we do when we're building a new BVH is, so after we've uploaded those Morton codes into the buffer, we also, into a buffer here, we also upload the ellipsoid indices such that, so it's in another parallel buffer to this one, so that when it sorts the keys, which are the Morton codes, it also will sort a payload buffer alongside into the same configuration. So if index 3 moves to index 0, so will this one as well. So I've got this GFX sort with payload. This is the first thing we do when we're building the BVH on GPU. So the next thing this paper says is you cannot have duplicate Morton codes. And it says here, the duplicate keys require special attention. This is discussed in section 4. Now in section 4, it goes and suggests a couple of things like, on how to, where is it? Let's just get to section 4 and just, string concatenation. I hate that terminology. Tend to use mixtures of spheres and ABBs most of the time, though. Right. The Z order could be fast as well. I haven't tried that. Fair play. Oh, are you talking about when it comes to sorting the in 3D space? I'm not sure. Right, okay. I thought it was like a new ray tracing method or something. Or a new acceleration structure, or a different acceleration structure method. Right, so in this paper, it says that duplicate Morton code keys have to have some special attention. And it suggests a few ways of handling that. But, it says basically if you've got a couple of keys, it says that you can basically concatenate the index of the node onto the Morton code key, and that will solve the duplication problem. But the issue is only have 32 integers, and if you concatenate them, it becomes 64-bit ints. But it says, in practice, there's no need to actually store the augmented keys. It is enough to simply use the indices of the nodes as fallback if two keys are equal. Two Morton code keys are equal. But I tried that and it just didn't work. So the way I decided to tackle this problem was to make a uniquifier shader, which we're going to now. So this is me launching my highly parallel uniquification shader, or the uniquifier shader. It basically takes in a buffer as source, which is the ununiquified buffer and of Morton codes, and then it takes in the destination buffer where to write out the uniquified keys. So basically this doesn't reorder anything, because remember we've sorted it. We cannot reorder it because if not the indices would be in the wrong place. It simply makes sure that any duplicates get incremented, and then if any more after that are duplicate, it increments those too. So we're going to check out how this was achieved. This was my own custom algorithm. I was quite happy with it actually. I thought about it all by myself. So we're going to describe it with diagrams. So I had to do some more shit. That's cool. No worries, man. But yeah, I thought it was when you suggested it was a new way to do ray tracing traversal, but by the sounds of it, you're saying it's a way to find stuff that's near each other in 3D space, right? Is that what you're saying? Why am I doing it? I should do it all in code. I had to think. Right, I gotta remember this. So imagine if we have 1, 2, 3, 3, 4, 4, 4, 5, 8, 10. Right. Well, let's do 9. Oh, wait, I want to do a few other bits as well in it. 88, right. Okay, so here we go. So I get to describe my super awesome shader. It's amazing. Right, so here's how the unifier works. So each thread, so we've got 32 threads in a thread group or a wave. So each thread gets an index within the buffer, the source buffer, right? And the basic idea is it takes the one that it is. Nah, right. You know what? Let me just let me just read the code and figure out some more. Okay, so it copies it over, puts it in there, right? With a max, which I get into later, obviously, and then it does a. It says if the left one in the source buffer is not equal and the right one is equal, I am the one who's going to be allowed to carry on right and do more copies, right? Yep. So then it will march to the right, incremented in the Morton code and the index. If it goes out of bounds, break. If then you get the source one at that index. If the Morton code is less than the next one, but if it's not less than, then we set it to the Morton code and we keep marching. Oh yeah, legit. Right, so how this unifier works is this is the source buffer here, and this is the destination buffer that we're going to be writing to. So every thread within this compute shader, where we've got 32 threads per thread group, but the thread group doesn't really matter. You know, we launch as many thread groups as we need for the whole array. And each thread gets a element within the source buffer. So every thread at the same time, or maybe at different times, depending if they're in the thread group or not, the same thread group or not, it will copy its one over to here, right? So let's do this one here. Copies 3 over to here. Then its next job is to say, right, I'm going to look to the left in the source buffer, and if the left is not equal to me and the right is equal to me, then I am allowed to march to the right. And you know, my brain started asking me questions, so I need to figure out. Because my brain was like, "Oh, is there a bug here?" But I've thought this through many times, and anyway, let me just satisfy my brain for a sec. So it does a max. And then, so what happens if the ones at the start and they're incrementing and then... Yeah, it's all fine because the ones here could start and we'll set those things there. But then if the one here comes along afterwards, then it will simply overwrite them and keep going until it can stop. Yeah, okay. Right, let me do that again. I've convinced President Henry this is all okay. You mostly use it as collision proxies for dynamic scenes, i.e. self-collision or inter-object collisions. Then you need to focus on extending your proxies when something moves from one frame to another, right? So it's used to find possible collisions over time without missing intersections, assuming your collision is working, right? So basically you have bounds for all your elements of interest, then merge elements close to each other where you are, then extend the bound, right? Okay. Right. Yeah, so what makes it different from a BVH? Because it sounds, it sounds like, yeah, I'm not quite sure how's it different from a BVH. Because it's still a tree, right? Right, so let's take a look about how this unifier shader works. So effectively, right. Right, so let's take a look about how this unifier shader works. So effectively, each thread gets a source, an element in the source array, and then this is the destination array here. So it gets an element in the source array, and the first thing it does is it goes, right, I'm going to take my source element and then write it into the destination element. Now it doesn't just assign it, because multiple threads could be writing to the same place in the destination array, it actually does it with an atomic max. So it takes the molten code, atomic maxes it here. So you ought to remember that this destination array must be zeroed, and if it isn't zeroed, then it's going to not work. So after we've copied it, the thread is going to be like, right, I'm going to check to the left, and if this one is not equal to my one, and if the right one is equal to my one, then I'm allowed to march to the right and start incrementing the ones to the right of me. So basically it carries, so it will end early if that is not true, right? So if it's not equal, if the right one's not equal or the left one is equal, then it's just not going to actually start marching. So this is to reduce the amount of things that march, because if you had a bunch of threes, these two threads will start marching and incrementing as well, and they'll be trying to write to the same locations. So to reduce the amount of things that march, only the ones at the start of the duplicates will be allowed to march forward. And the basic idea is that we increment our Morton code, storing a little local variable, and we check to see if this source, or if this source entry is less than or equal to R1, our current Morton code that we have, which is 4. And then, so because it is, it will actually atomic max that one in there, and then it will increment, do the same thing again, read this one, right? Is this value less than or equal to the 5 that we have? Yes, it is. So we'll write it in there, right? Is this one less than or equal to? Yes, it is. Our 6. So we'll put our 6 in there. And then is this one less than or equal to? No, it isn't. So I'm going to stop now. So obviously that was just for this thread. But you can also get this thread here. These threads here, which would have simply just copied their value into here and then returned, because they do not have a duplicate to the right hand side of them. So they would have atomic maxed it in here. So even if this thread ran along and started writing into the same location, the maximum value would always win. So it's safe. So let's just take a look at that in code form. So after it writes the value into its own location, and it is the one which has a duplicate to the right but not to the left, it's going to increment the index and the Morton code, and then if it's out of bounds, return, and then it gets the next Morton code from the source buffer, right, not the destination, the source, and then it will, if the Morton code is less than the next Morton code, it just breaks, right? But because this, because it's actually greater than or equal to, it will write it into the destination buffer here. So you might be thinking, well, what happens if there's another duplicate? Just undo this a bit. Yeah, so what happens if there's another duplicate that wrote into this buffer? You know what, I think that's enough explaining. I think that was just good enough. They can read the code if they're interested. Right, so that's how the uniqueifier shader works. Right, so that's how the uniqueifier shader works. Yes, it's a tree. Then there is more to cluster the elements. I don't want to divert you away from your goal there. It was just something I'd used in real-time dynamics. Yeah, I've never heard about it. I'm interested to learn about it though, because every time I Google like I've never heard it used at all. Oh, is it the same as a KD tree? Because this algorithm implements a KD tree as well. I guess it is the same as a KD tree. Right, I've heard of that one, but I don't quite know what it is. RCT, how's it going? Parallel locally ordered clustering. Oh, I got linked to this one at work. Yeah. It's very interesting. I need to understand it, to be fair. So initially we assign one worker per leaf node and follow the LBVH hierarchy upwards. Interesting. Atomic exchange? What? Bananas. Oh. You could tell it's like a crazy cool algorithm when it's got a bunch of wave intrinsics. It's not too long, to be fair. What's the results like? But I wonder what the traversal is like, because as well. Yeah, I wonder what the build performance is like. Sorry, the traversal performance versus build as well. That'd be interesting. But yeah, thank you. I'll take a look at that one. Or I'll try and understand it at least. Right, so here's my uniqueifier shader. I spoke about that. What's next? Right, so after we build a binary tree with the algorithm suggested in the paper. Right, so the next thing we do after running the uniqueifier shader, so we've got those Morton codes all nice in an array, is we follow the paper and we build a binary tree. We build a binary tree, right? What is? Right, so the next thing we do after we have uniqueified all those Morton codes is we build a binary tree using the same algorithm as that paper has suggested, which we'll get into in a sec. But afterwards we build a quad tree from that binary tree. So just to show the data structure for a second, BVH node, there we go. So we've got this thing called a BVH build node. It's not really that optimized at the moment, but it's basically like one that gets built is we build a binary tree with it first, and then we turn that binary tree into a quad tree. So we use the same data structure and we're just mutating it a second time around. So it's got a parent index and it's got a few other things which we'll touch on later. But I just wanted to explain that we use the same data structure and it just has the capacity for 4 child indices. Right, so let's get to the paper. So the paper How does it work? Right, so the basic idea of the paper is there's these things called leaf nodes, which are indexed differently to internal nodes. Right, so leaf nodes are obviously those ellipsoids that we've seen in the scene, and the internal nodes are the non-leaf nodes. So they're everything else. So they're the parents of the leaf nodes and parents of other parents. So the way that the paper kind of works is that every node can know where its left and its right child is with only just looking at the Morton codes of the leaf nodes. And that's all it needs to know. It doesn't need to look at any of the other internal nodes. It simply just needs to read the Morton codes and run some logic on that. So effectively, the root node is always 0 here. And something to note is as well, in our implementation, our leaf nodes don't technically have index 0 as well. They technically start after all of the internal nodes in one big buffer. So, but we sort of just know how to identify what is a leaf node because it starts after all of the internal nodes in memory, right? So it starts at 7. So we just do, node index take 7. It gets us our leaf node index. Right, what's the other thing to take note of? Oh yeah. And also in a binary tree, you can know exactly the number of internal nodes you're going to have just by knowing the number of leaf nodes. So here we've got 8 leaf nodes. So simply it is just, 8 take 1, and that is the number of internal nodes you'll need for a binary tree. So with this information, you'll be able to allocate enough room in a buffer for you to put all of your nodes, right? So it'd be number of leaf nodes, take 1, plus number of leaf nodes, and there you go. So with this highly parallel algorithm, the way it basically works is that, say you've got this node 2 here, internal node, we're trying to find the children for internal node 2. And all I can do is look at this bit pattern. So the basic idea is it finds the range of the children node, of the range of nodes that it will be addressing. And then after that, it looks within the range of nodes that it will be addressing and finds where to place. Let's record that again. Yeah, don't worry, get you, man. Thank you, Code Nugget. Appreciate it, sir. We also have a Discord, by the way, if you want to come and chat in the meantime. Yeah. That's cool, though. Right, so at a high level, basically how this algorithm works is you take, every thread on the GPU gets an internal node it's got to find a left and a right child for. And the basic idea is that it first has to determine the range of nodes that are going to be under it they're going to be descending, right? The descendants of this node. So in this case, 3 here determines a range between 0 and 3, right? 0 and 3 here. And then after that, it finds where do we place the split position, and it will place the split position after that within this range at 1, right? And then basically that's the left node, then the right node is simply 1 plus 1, right? It's just adding 1 to the left node, and that gets you your other node here. Now there's another little thing about it as well. So yeah, okay. Right, so you might be thinking, how does it possibly, if after you find your split position, if the right hand node is just +1, why don't we link to this 2, 1 down here? Why do we link to this one here? Well, that is because the way the algorithm works is if your split position is at the beginning or the end of the range, then you link to the child. Right, so you might be thinking, why when we add 1 to this left node, do we take this other internal node here? Like, okay, so better ways of saying it. Right, so you might be thinking, why when we found the split, did we decide to use internal node 1 and then add 1 and use internal node 2 when there is a 1 and a 2 here for leaf nodes? Well, because the way the algorithm works is that when you've found your split, effectively, if the index, the left node or the right node, is equal to the start or end of a range, then it will use the leaf node instead. So this 3 here, when it splits, it just has a 1 and then a 2, and obviously these 1s and 2s are not 0 and 3, so it just uses the internal nodes. Whereas this 2 node, when it finds the children, its children are pointing to 2 and 3, and because 2 and 3 are matching the 2's at the beginning of the range and 3's at the end of the range, well, therefore it's going to select the leaf nodes. Now on this right hand side is a bit more of a different setup. 5 here has a split at 6 and 7, right? But its range is between 5 and 7. So that means that, when it's left, its left is obviously, it finds the split at 6, and that's where the left one is. So that's not at the beginning or end of the range. But when it adds 1, 7 is at the end of the range. So it will select the leaf node instead. So it's just a bit of maths, just to add on the number of internal nodes, and then you've got to the leaf node basically. Right, so here it is in my code here. I've implemented that determine range function, which passes in the Morton codes, passes in the number of leaf nodes, and then it passes in the internal node index that we're trying to find the children for, right, that parent node. And it gets a range of descendant leaf nodes for this internal node. Then we use that range to go into here with the leaf nodes as well, and we find where do we split within that range. And obviously this would be the left child node, which is the split point. And so yeah, the left will be equal to split and the right is split plus 1. And then we basically go, well, if the left hand side is equal to the start of the range, then we just add the number of internal nodes and that gets us to the leaf nodes. And then the same here as well with the right hand side. If it's equal to the end of the range, then we just add I'd want them. Sorry, add the internal nodes, and then gets us to the leaf nodes there too. Right, that's pretty alright. So do I want to go and describe much about how the rest of it works? You know, there's a whole paper covering it. I'm kind of just giving an overview. You know, I've talked about the Morton codes, but it basically scans down the Morton codes and finds the bit where it differs, and yeah. Do I want to go and explain this code? Yeah, right, okay. I'll just say I won't bother explaining it. But yeah. I've given enough sort of clues around it. They can read this stuff. Right. But yeah, I'm not going to go too much into how the determine range and the find split works here today. But yeah, you can check out the blog if you're interested in finding out, and also read the paper as well, because it goes into exactly how all that works there. Right, so let's talk about the next stage. But we should show more diagram, or pictures now, because like we've been seeing other material. Let's just show like join the Discord. Have to leave. Interesting work. I have many years with surgical simulators implementing soft body dynamics in real time. Awesome. Sounds really cool, man. Be interested to see some of your work. But yeah, open up a chat in there, and it'll be good, man. Right. I'll see you. Have a good evening. Yeah. I'll see you soon. Awesome. So I want to show that tree in it, but we're showing a, hang on a minute. There it is. I want to show the binary tree instead of the quad tree, because we've just shown how to build a quad tree. Right, so after you implement that paper, you basically get this quad tree which can be built, where each node can be built independently, which is super cool. And I highly recommend you build something like this so you can debug it. Here we're visualizing those Morton codes down each leaf node, right? And we're able to reason about the data and make sure it's all correct. And we're constructing this tree in a highly parallel manner, and then traversing the tree from the top down on the CPU, and just trying to draw the whole tree. And if the whole tree doesn't draw, then the code is wrong. But yeah, it's been super helpful just to debug everything and make, and if it doesn't work, I can debug it a lot easier on the CPU, right? Yeah, I think that's good enough. So we should talk about how how I decided to build the quad. Yeah, this is another Henry special algorithm. Yeah, so how did we build? Right, so the next thing we do is we take that binary tree and we change it into this quad tree here. So rather than having a parent having exactly 2 nodes when it has children, it's going to instead have 2, 3, or 4. And I'm going to describe the algorithm that I basically just came up with on the fly and how we implemented that one. Right, so I've got to remember how I implemented it. Step 1, remember what past Henry did. Build quad tree. So, oh yeah, the grandchildren. So when you get 3 or more grandchildren, you say, I forgot it now. Oh yeah, start off all the leaf nodes, visit the parents, mark up the visit count, up a visit counter. When you've, when you're the second one to get there, get the left and right node, count the grandchildren. If the grandchildren are 3 or 4, then you can do a thing, which is what exactly? Oh yeah, when they're between 3 and 4, we basically join them together. Yes, whatever they are. It's quite aggressive. It's good. And then this one is saying if they're greater than 4. Right, it's all about allocating those destination node indices. It's too many beans to spill if I just talk about that. So I think we'll just talk about the algorithm with pictures. Pictures. Oh. Where's my binary tree? There we go. Right, so the way the quad tree build function works is it takes in a binary tree. So it's a shader that runs another compute shader where each thread gets a leaf node, and all it's going to do is mutate the binary tree and see if it can start deleting nodes and bringing the children up a level. So let's talk about the traversal part of the algorithm, or how we traverse up the tree, and then we'll talk about what we do as we traverse up the tree. So each thread gets a leaf node, right? Not an internal node, which is these guys, but a leaf node, one that doesn't have any children. So every thread goes up to the parent, and there's this thing called a visit count, and it ups the visit counter with an atomic add and gets back a result. And if it is the last child to reach, so remember it's a binary tree, if it has a child, it always has a sibling, right? So this means that there's always 2 children or there's no children. So it goes up to the parent, ups the counter to 1, gets back a 0 because that's what it was before. Then this one goes up at the same time, probably ups the counter, and this one gets back a 1 because it was the second one to go through. So now this one is allowed to carry on. This guy has to terminate and doesn't carry on. So the ones that set it a second time around get to traverse up the tree and keep going and repeat the same thing again. Goes to the parent. Am I the second one to be here? Yes, I am. So I keep going. But if I wasn't, I will terminate here, right? So this defines a way to have a highly parallel tree walking from the leaf nodes all the way up to the root node, and there will only be one thread which will reach the root node, right? So this means that there is one thread that reaches the parent, and then when it reaches the parent and, all of the descendants don't have any threads on anymore. That's what this algorithm guarantees. So what we can do is we can essentially say, right, how many grandchildren do you have? And how many grandchildren do you have? These guys don't have any, but they're going to return 1 instead. So leaf nodes return 1. So this one goes, right, do I have 3 or 4 grandchildren? And if I have 3 or 4 grandchildren, what I'm going to do is I'm going to take my left node and my right node, and I am going to get rid of them if they have if they actually have any grandchildren, and then move the grandchildren up to being children. So in this case, nothing happens because there's only 2 grandchildren, if you will, that got returned here. So it's gonna now go up to this parent and up the visit count, and turns out it's the second one to get there. So now it's going to look at these children and ask, how many grandchildren do you have? So this one says, I have 2 grandchildren. And this one says, I have 2 grandchildren too. So what it's going to do is report that back and it adds them together. And in total, there's 4 grandchildren, which is perfect. Because what it can do then is delete this node and delete that one, and make this one, this one, this one, and this one children of 5 instead. So essentially just unlinks 1 and 2, and then it will make these nodes children of 5 by patching the parent indices and the child indices. Now, we kind of start from a bit of a funny place, because technically these guys would have been joined up here actually. So how it would have actually worked is 3 would have been deleted, because it would report back 2 grandchildren to 4, and then 17 would have reported back 1. So this would have said, hey, there's 3 grandchildren, so it will, add that 1 back to the child indices, delete this 1 and add these 2 in. So 4 would have these guys. Then 2 here would ask for how many grandchildren it has, and it says, oh, I have 3. So it's there's 3 nodes there. There's its 3 nodes, and it asks the right one how many grandchildren, and it has 1. So 3 plus 1 is 4, so it can now join these guys. So this whole region here actually gets collapsed into just one node called 2, with children 17, 18, 19, and 20. So then actually 5 would not join up, but with this one. But that's but that was just an initial example. Right, I think that was a good explanation. Hey Vance Pebble, yeah, I'm using an Arch-based distro. I use Manjaro. Many times in the past I've set up Arch, but I just wanted something a bit easier to set up. So I just installed Arch and Manjaro, and I uninstalled a few bells and whistles, but does a good job, I think. Right, this is getting really good. So I think we're nearly there now. So we've got a quad tree built. So we can talk about that one. So again, I built this on the CPU, bearing in mind how it would have been implemented on the GPU, and did it the same way. And so we can visualize it here and make sure it's all correct. So what's interesting is we're seeing it here, right? Here's that 1 and 2 node, right? Remember 1 and 15 and 16 were here? And remember there was that group, 2 had a bunch of, had a bit of a family tree going on, some descendants, but then it kind of made it more flat, that 17, 18, 19, 20, right? So there's the algorithm working in practice. So yeah, again, this was super handy to debug everything and make sure it all works fine. By implementing it on CPU and then simply traversing down the tree and figuring it and just drawing it and just making sure every node was there and there's no node missing. Right, so what's the next thing that we do after building a tree? Oh, I get to talk about my packed nodes now. Let's go to my shaders. No. Code Uniquify. Here we go. Right, so we're nearly there now. The only other thing left after building the quad tree from the binary tree, remember we just mutated the build nodes, right, and just added more nodes in there. We didn't actually build a whole new tree, we just mutated an existing one. The final thing that we do is we pack the quad tree into more of a optimized format for traversing. I've not done any big performance tests on this, but I've just followed my sort of previous experience on this stuff, but there's still tons of optimization to do and also comparisons with different, things. So effectively this one takes in the build nodes and outputs like the packed build nodes that we actually used to traverse. And we've still got to, write a custom allocator on the CPU where it's just going to allocate a sub-region of the massive BVH nodes buffer where it fits a tree of nodes into that buffer somewhere. So let's take a look at the packed node. So this is the unpacked node, right? It's got that visit count in there that we saw earlier. Hang on a minute. My brain. Right, so it said, yeah, so we need to say that like visit count is, the visit count is used in the, oh yeah, I want to talk about that. Yeah, okay, I'll get back to that afterwards. That's good, that's good. Right, so what did I do now? I said, right, so let's take a look at the, I didn't even know how I did that now. Let's just redo the whole thing. Right, so after we've built that quad tree, remember we are building the quad tree from the binary tree, so it's just that same set of BVH build nodes. We are simply mutating the tree and not building a whole new tree structure. So after that, we need to pack the quad tree, and we're packing it into more of a optimized structure. So the data structure is more packed and hopefully better to traverse. So I've obviously not tested this, but it's just going off my instinct based on past experiences that this is going to be better. But yeah, I've still got to compare it when I do proper optimization in the future. So we output to another BVH nodes array. This is a big array, whereas the build nodes is just a little one just for building one BVH at a time. This BVH node is a larger one, and there's a BVH node start indices, so we need to write a custom allocator in the future on the CPU, which basically just heap allocates from a big array of nodes. And yeah, big array of nodes. So let's take a look at the nodes. So let's take a look at the build node for a second. This is the one we use while building the tree, obviously. So we've mutated it and, use more than 2 children indices now, and we've got potentially up to 4 children in a node. So when we traverse this node, this tree, Oh, should I talk about this now? Right, so this is that sort of packed BVH node. It is 16 bytes, right? 4 times 4, so 16 bytes, and we're packing a lot into here. So each BVH node is an ellipse, or an ellipsoid, shall we say. It's got center position, it's got half dimensions, it's got rotation, which is a quaternion, and we've also got 16 bits to reference a bunch of, or up to 4 child nodes, and we've got, if it's a top level BVH, which we're working on in the future, it will reference a child BVH, another whole BVH, and then if it's a leaf node for a bottom level BVH, it is a material index, so we can do all the lovely PBR shading. So this BVH node is, when you have 4 of them, it takes up 64 bytes, which is equal to a cache line. So the basic idea is whenever we've hit a parent and need to look at the children and test the child nodes, we test all the child nodes one after the other, and everything's aligned to 64 bytes. So when we start trying to work on the first BVH node, it will obviously have to fetch that cache line, and it's probably going to switch out the shader to another one and run that for a while. But when it comes back and it's got that in cache, all of the other nodes being cached as well, and it can just start operating all of those, and the bottleneck will then be basically unpacking and then doing the reverse ellipsoid test. So we've decided to go with ellipsoids all the way down, so we don't have different geometry as you go down the tree. We don't have an axis line bounding box and then ellipsoids. It's all ellipsoids all the way down. So here we've just got this initialize function which takes in the unpacked parameters and packs them all in, right? Just does some packing. And then we've obviously got some nice functions to unpack our data as well. So if we want to get the ellipsoid center position, we can do that here, or the half dims here. Right, what else? I want to talk about how we actually build it. Right, so how do we pack this quad tree? Well, it works exactly the same way. Well, not exactly, but basically the same way as when we build the quad tree itself, right? So rather than starting from all the leaf nodes of a binary tree, we're starting from all the leaf nodes of a quad tree. So every thread gets a leaf node, and then it does that same traversal technique where we go up to the parent, up an atomic counter, so that visit count. And when the visit count is equal to the number of children, so that means we're the last thread to get here, therefore we can pack the node. So we can then copy the build node, and we can start, or we can copy all of the children nodes, and we can start packing those guys in, right? We can, wait, that was wrong. That was wrong, that's not how it works. Packs itself. What did pass Henry do? Yeah, look over all the children and build yourself. Yeah. Why don't we ask him Yeah. Yeah. Sometimes I want to thank Past Henry, other times Past Henry needs to be taught a lesson. You know what I mean? Sometimes he gives me favors, other times. Hey Cat Payne, how's it going? How you been? How's things going? Right, so how do we build that packed quad tree on the GPU? How do we traverse the tree and do all of that? Well, it works basically the same way as when we build that quad tree. When we traverse that binary tree from the leaf nodes up, we do the same thing but with the quad tree instead. So every thread on the GPU gets a leaf node, right? And we just go up to the parent, up the visit count. But this time, when the visit count equals the number of children, we are the last thread of all of the siblings to reach the parent. So therefore, we are allowed to carry on and survive. The rest of the children threads just, return early and don't carry on anymore. So with that strategy, you deploy the same sort of thing where when you're the last thread that reaches the parent, you are allowed to copy the parent into, so you copy yourself and then you copy your, I did it again, didn't I? I started talking and then I didn't really fully understand it. You copy yourself, then you traverse up. Doing fine. Apparently there's a leak for the new RTX cards. They draw more power across the board. Isn't that just standard now for RTX cards? They're just gonna keep drawing more and more power. And then sooner or later they're gonna be a whole separate computer you have to plug in. And then, and then your PC will just be the GPU. No. I don't know. I should stop giving them ideas. Right, so how does this quad tree packing shader work? Well, it actually works in a very similar way to how the quad tree building shader works, but instead of traversing a binary tree from the bottom up, we traverse the quad tree from the bottom up and simply pack it into the new destination buffer at the allocated sections. So we start off at the leaf nodes, right? And we go up to the parent and up the visit count. But this time, rather than reaching non-zero, we have to reach the children count, right? So when we atomically add and then we add another one as well, and when it's equal to the number of children, it means that we are the last node to reach the parent. So therefore, we're allowed to carry on as the parent and go up the tree and repeat the same logic. The rest of the threads that reach here and are not, when they increment the visit count and it's not equal to the number of children, then they need to terminate. So how the algorithm basically works is each thread starts off on a leaf node. It starts in a loop, copies the current node to the new destination place in the array after packing it all. And then it will go up to the parent. If it's the last one to reach there, it repeats the same logic again, copies the parent or the current node to the new destination slot, and then repeats the same logic again. So with this algorithm, you can then build you can pack a quad tree. But something I left out is every time you do the whole packing thing, you're not just simply copying stuff around. I'm actually computing the boundaries of all of the children and producing the bounding box for the parent node. So 2 here, while it's doing the packing, it's also going to work out what is my ellipsoid for this node. Goes over all the children and works out an ellipsoid that covers all of the children. And then it packs that into the packed node. Okay, so this is where I can talk about my super simple but meh node thing. Node, yeah, whatever. Ooh. Right, so part of the BVH traversal code, we have a visualization of when we hit a parent node, and we've got this sort of like outlined ellipsoid that I quickly threw together with basically the normal vector, so it looks a bit like a thin strip, like a ribbon. So effectively, the way we calculate the bounding box for 3 is we go over all of the child ellipsoids and we compute their bounding box. So their bounding box is just the half dims, where it's the radius. And then what we do is we find the maximum and the minimum point of all 4 corners, and we keep that minimum max for I've got to do that again, innit? Yeah, I could have just said it that way. I don't know why I did that. Why not put those ellipsoids in a BVH? What? They are in a BVH. Get pain. Sorry, I don't understand the question. But yeah, they are in the BVH. This outer one's in the BVH. And then these are the leaf nodes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 3 is this red one. Boom. No, why? Because then I won't be able to see the child nodes. No, I will, because it's in the BVH. So let's take a look at how we currently construct the ellipsoid of, or the parent ellipsoid of a bunch of child ellipsoids. So as you can tell with this tree, we've got 5 leaf nodes, 1, 2, 3, 4, 5, right, 5 ellipsoids. And then what we have is a parent node, which is 3, and it's wrapping around these 4 here. So all we do is we just currently go over all of the children here and produce a axis line bounding box, which is very simple. It's just the half dims of the ellipsoid, or the radius that we already have, basically. So the half dimensions of it. And we use that same thing as the bounding box, and we produce the minimum and the maximum coordinate between all of these shapes. So it'll get you something down here, it'll get you something down here-ish and something up there-ish, and produce a big bounding box around all of them. Now the problem with using ellipsoids as a parent is when they bend, they actually go in and they don't, the ellipsoids won't be flush against the bounding box anymore because the corners will go in, right? The corners go in like this, they curve in, therefore the bounding, if there's ellipsoid here on the edge, it will be outside of the ellipsoid now. So what we do for now is we just multiply it by this the maximum half dims of the new ellipsoid by the square root of 3, and that just does a good enough job for now. But it's not good implementation in the long run. In the long run, we need something better. Rolls to the better implementation that it's still got to implement. Bum bum bum. Discord time. Bum bum ba-dum bum ba-da-ga-da-da-ga-dum dum bum 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 bum. Right, so I raised the question in my Discord and asked basically, has anyone got any good ideas on how do we produce an outer ellipsoid around a set of child ellipsoids? And Albert here managed to find there's this blog post, and it basically produces an oriented bounding box, which is what we want. Basically, we want to orientate, like we support a quaternion to sort of rotate an ellipsoid anyway, so we'll be able to rotate that parent ellipsoid and find the best fit basically. So I'm not sure exactly the way it does it, but I've got a general idea. I've still got to read over and actually implement it fully. But the basic idea is you take all of the points for the child ellipsoids and you essentially you somehow take the vertices and you use a matrix, and with some maths you can essentially produce an axis and the width and height and the depth of the orientated bounding box along the axes apparently. So we should be able to produce a lot nicer packed or a lot nicer ellipsoid, but the issue still remains where it's an orientated bounding box, so therefore we need to multiply it by the square root of 3 or something so we can produce an ellipsoid which wraps around the bounding box and it goes a bit outside. Now, as you can tell, these ellipsoids are not a perfect it's not perfectly wrapping around the other ellipsoids. So we've got to think about ways that we can maybe improve on that part of the algorithm. Maybe we can, I don't know, use a sign distance build function and shrink it by that. Maybe there's some other ideas that we can think about as well, but that's where I'm at with that one. Sweet. Yeah. And he, left a link to a blog post, so I'll leave that down in the description if you're interested, which goes over this algorithm here. Right, I think I'm basically there in it. I'm not going to talk about the BVH traversal stuff because it's not even finished yet. But that's cool. Success. Has anybody got any questions? Anybody got any questions? Is it 16? Let's figure out. Buddy. Oh, it's 15. So I think I tried to do 15 before and then I was like, screw it. I'm gonna wait until I've actually implemented the whole damn thing. So, after we've recorded this outro, I'll talk about what we're doing next. Come again. New renderer. What does new renderer mean? What did past Henry do? I didn't do anything. Oh yeah, I just got one BVH, one ellipsoid rendering. Yeah, so I guess I'll say 131. What the crap's going on? Boy. Oh. 131. Why is that one called new render and it says 14? I changed it to 15. I think I start. Okay. I think I understand that. 131 to 138. 7 streams to the bottom level BVH implementation. Felt longer than that, to be fair. It's a couple of weeks, wasn't it? Bow. Right, so it gets to the end of the video. Thank you so much for watching. So that's devlog 15. If you check out the VOD channel, it's day 131 to 138 if you're interested in seeing more of the nitty-gritty details. Yeah, so if you want to watch this, the streams live, we do stream this live on Twitch Tuesday, Thursday, and Sundays. You can check out the schedule on Twitch to see it in your time zone. And there's a VOD channel where you can catch the VODs after the fact. And there's also a Discord channel if you come and hang out in the meantime. If you're interested in source code access of the game that we're building, you can sub via Twitch or via Ko-Fi. Ko-Fi is much nicer for me. There's more of a kickback. You'll be able to get access to the code on Windows and Linux and also help me in the process. Thank you for everyone who's already supported me, and I'll see you guys in the next one. That was pretty smooth, wasn't it? So, what are we doing? What are we doing next? So obviously, we've built a bottom level BVH. Let's get some visual in our faces. So bottom level BVH is basically an instance. So if you have static geometry and it doesn't move, you can have like essentially it's like a mesh, right? You can keep that one BVH around and you can instance it as many times as you like and just reuse the same BVH tree. But as soon as it becomes dynamic, you need to make a copy of that BVH. Then you need to do all the refitting stuff. You need to make a copy of the BVH. You need to do all the refit stuff every frame when it moves. And what else? Yeah, so you cannot utilize sharing of the same BVH structure. We're going to save that stuff later on because we want to be, or rather would get more of a kind of a scene, have the ability to have more of a scene, and then we can try and get animating working. after that. So what we're going to be focusing on is the top level BVH, which basically links to a bunch of bottom levels. So the leaf nodes, instead of being ellipsoids in our case, they're actually just going to be a bunch of, it's going to be, the leaf node is going to be a whole instance within the world. So if we build that, we can then have multiple instances of the same BVH across the whole, across our scene. And we can work on like the custom allocator for our nodes and other things. Oh, and also improving the traversal function, because right now we just traverse in a very small set of nodes. We want to try and up the number of nodes and just try and traverse more, and just see what we can handle with our current implementation, see how we can improve that as well. So that's what we're going to be working on over the next, I guess. Top level is probably going to take another week's worth of streams, maybe a bit more, a week to 2 weeks, and then another week to 2 weeks again for the animated ones. And after that, we should have all the BVH stuff done, and we can move on to doing non-rendering stuff. Kept paying, my friend. Thank you so much for the sub. Appreciate it. Appreciate your support, man. Appreciate your support, sir. Hope things are going well for you in your life. Give me some updates. But yeah. And then after, so maybe in a month's time, maybe less than a month's time, anywhere from that region, we'll be putting a pause on rendering stuff and going back to the game engine and then building up some form of editor which allows us to construct the BVHs in some form of editor, and we can start building things. Because I think it's time that we start making an effort on building some test scene that we can then come back and do more rendering stuff with. Maybe you want to do more rendering. It depends how well this current rendering setup works. Maybe we do more game stuff. It depends how I feel, to be fair. But yeah, that's what we're going to be working on soon. Right, so there's a Discord if you can come out, hang out in the meantime. And I'll next be on Sunday at 6:30 or maybe 6 p.m. GMT +1. It depends. It depends on things. Somewhere about that time. Let's find someone to read who's programming in something sensible. What's going on? Damn it, Twitch. Well, I don't want to know about Prime Gaming stuff. Come on. Is it my dark mode? I don't know. TypeScript. What? Game development in TypeScript? Maybe he's got a server. That's what's strange. Unreal. Wait, where's that zig guy? The zig guy's gone. Yeah, similar or small, let's do it. Yeah, I'll see you Sunday. Good to see you. What? Right, I might just bail. I can't find anyone. But yeah, thank you for coming, guys. Appreciate it. Have a good start to your weekend. I'll see you all in the future one.